Let me quickly check if we're live on YouTube. Should be good to go, I believe, in just a second. Nope. Okay, we're good to go. So let's start. Hello, everyone. Welcome to today's developer call, where we'll talk about solutions for Performant Layer 3 app chains. My name is Robert, a developer advocate at the Starknet Foundation, and I will be your host for today. Here, I'm accompanied with a few wonderful guest speakers. We have Dr. Karthik from the Duke University and Decentralized Thoughts, Luke from Web3 MQ, a Layer 3 infrastructure, Itai, Chief Architect at Starkware, and finally, Manmit, Developer Advocate at the Starknet Foundation. Welcome, gentlemen. I'm super excited to have you here and learn more. I would like to go around the room and quickly give a few, introduce the speakers. So maybe we could start with Dr. Karthik. Would you like to give a short introduction about yourself and what you're currently working on, and then we could go around?
Sure. My name is Karthik Nayak. I'm an assistant professor at Duke University, and I'm also an advisor at Espresso Systems. So my research focus is in applied cryptography and broadly blockchains. But within blockchains, I focus primarily on consensus protocols. And with consensus protocols, I guess there are many things to optimize for. There are the core metrics. Things like latency, communication complexity, adversarial tolerance under different network conditions, and the kind of adversaries that you tolerate as well. So I think I focus on all of that, as well as I focus on how consensus interacts with the rest of the ecosystem. For example, how something like MEV can play a role, or something like privacy can play a role, how that interacts with consensus. So I mean, so that is the primary area of focus for my research. Thank you.
Got it. Thank you. Maybe we could go to Itai and then Luke and Manmit.
Hi, I'm Chief Architect at Starkware. Been working at Starkware for a year and a half now. I joined from Akamai, where I was a Chief Architect for 10 years for the Web Security Division. That's it.
Thank you, Luke.
Hey guys, I'm Luke, part of a team called Web3MQ. We've been building for about a past year, really heavily around blockchain infrastructure. Before that, we were slightly more focused around just messaging, just high performance, trustless messaging. But right now expanding to more orthodox and classic blockchain infrastructure. We've been upgrading the consensus layer from Madara, which we'll go into maybe a little bit later on, but also we're also trying to build something more as a slightly upgraded version of shared sequencing for, Dr. Karthik has mentioned Espresso, but also for L3s on Starknet based on Madara. So we call it the Nomos layer, but if people are curious, we could talk about that later on too. Yep.
Thank you very much. Manmit?
Yeah, so I'm the developer advocate for the Starknet Foundation to the US, and I am essentially responsible for helping developers, Web3 developers, people looking to transition to Web3, learn about the Cairo Starknet tech stack, learn about it, and find meaningful opportunities in the Starknet ecosystem here in the United States. And yeah, it's a big moment for me because I was a student at Duke University where Dr. Karthik Nayak actually taught me about consensus and blockchains. And then Itai and Luke have been, were part of the team at the company that I started working at right out of college. So yeah, super excited to be here.
Great, awesome. And we have Matan and Felix. Could you give us a short introduction about yourself and what you're currently working on?
Sure. I'm Matan. I work at Starkware as a software engineer, and I'm currently involved in the effort to develop a consensus for StarkNet and help it become a distributed network.
Yeah, I'm Felix. I'm currently working with Manmit in the StarkNet Foundation Fellowship, and we're working on combined distributed system and recursive ZK proof to scale machine learning and data analysis. ZK machine learning and data analysis. Thank you.
Great, awesome. Great to have the introduction from everybody. Super excited for today's topic. Maybe before we get into the solutions for Appchains, I will give a short introduction about Appchains. So basically, they are application-specific blockchains that are designed to service the needs of one specific application. On StarkNet, we have this StarkNet stack, which offers a great variety of and diversity of services, such as full nodes, sequences, provers, etc., and also gives the possibility to spin up an app chain seamlessly. And now, like with Appchains, you can customize a lot of things to serve your specific needs, such as different hash functions or consensus mechanism. So on this matter, I would like to ask Luke, maybe you could tell us more what's the vision for Appchains at Web3MQ, and maybe talk about Nostos Network and Madara.
Yeah. So everything we're building around Nomos and whatnot, it's all on the Madara stack, and it's actually a layer, so anybody can use it together with the Madara stack to build their own app chains. Essentially, what we're doing that's kind of new is, so I guess for app chains, we're imagining about two audiences maybe at this point that are just really, really key. One is, I think, DeFi. The other is things like games and whatnot, and like really high performance, but maybe slightly less focused on the financial consistency. For DeFi, I currently kind of think maybe it's around MEV properties that might be super nice if optimized. For games, obviously, of course, people want high performance and less of a kind of a strict focus on transaction ordering and whatnot. So DeFi, you might be able to run bigger, but we kind of see one possible future where app chains, they work for an app, right? So they're a lot smaller than L1s or L2s. There's a lot less incentive for operators first to run just for a single game or a single DeFi protocol. If you're running an operator for StarkNet, well, you're serving tons of applications, right? Possibly thousands. But for an app chain, you're serving one or two. So for Nomos, we're all kind of familiar with shared sequencing, right? Where we want to kind of share that block building layer. But also we kind of feel that, since app chains are so small, there's this pain point where one, for operators, there's less incentive for you to operate these things. And also for the game or the DeFi protocol, well, people have to go through the process of finding a network of, say, 100 or 1,000 operators to actually operate that app chain network. And that's, that makes way less sense, right? Like for Ethereum and for StarkNet, it makes a lot of sense to gather those things because it's a relatively bigger platform. So instead of just sharing that sequencing layer, we do also want to make the app chain itself somewhat virtualized and make it possible to share that execution too. So that's a really brief kind of addition that we want to add on top of like capability that we want to add on top of the Madara stack so that applications can just really spin up their app chains a lot easier. Yeah.
Great. Thank you very much for that description. And now I kind of like to start building the topics around consensus. Maybe Dr. Carter, could you tell us more about the Byzantine fault tolerant state machine replication, or short for BFT SMR, in distributing computing, and maybe some of the top protocols?
Sure. So if you're thinking about state machine replication, right? So what are you trying to do? You're trying to maintain a state machine somewhere, and the simplest form of a state machine, maintaining a state machine is, there being one machine which takes in client commands, processes this client commands as per the state machine, and gives you responses, right? So the key problem that you're trying to tolerate over here is there being potential faults in the system. Right. So if the system were to be live, trustworthy all the time, that is all you want. You don't need anything more. So the problem is this machine can fail. And that's why with state machine, so instead of just using a single machine, a single server, you replicate the server. And so when you replicate, the hope is that you are able to tolerate some faults, even if some of these machines break down or they act maliciously or crash or whatever, you still can run, the entire system would still function. But at the same time, that brings in a challenge, and that challenge is that these machines need to be consistent with one another. It cannot be the case that one machine tells you something, another machine tells you something else, so that a client does not have a consistent view of what has happened. And that is where state machine replication, so that is where you use state machine replication. So the crux of a state machine replication system is where it should give you the same interface as that of a single non-faulty server, in that it should take commands and respond to commands. So if you're thinking about the system as a whole, right, I think that there are two key properties that the system needs to uphold. And this is what we refer to as safety and liveness. So intuitively speaking, safety says, nothing bad can happen, and liveness says something good will eventually happen. So what does nothing bad can happen mean? You do not want two clients to have different views of what has happened. Or if I think about it from the standpoint of the replicas, you do not want two honest or non-faulty servers to think of two different transactions being executed at a given position, for instance. Or if you're thinking about just agreeing on one thing, they should not disagree on what has been agreed upon. That is the core thing that you need with safety. And liveness says something good will happen, which says, if you receive these commands, you will process these commands. So note that, achieving one of these two properties is very easy. So if you just want safety, just do nothing, and nothing bad will happen because no one will disagree, but they have not agreed upon it. They have not attempted to agree upon anything. Similarly, if you just want liveness, that is very easy as well. Process, every server replica just processes whatever it wants, right? It's getting the combination that is interesting. So when you think about state machine replication, there are many factors to consider, and over here, I think I'll mention a few, but I'll also give a shout out to, there's a blog that is maintained by my collaborator Rita and me, where and a bunch of other researchers actually, called Decentralized Thoughts. So if you go to decentralizedthoughts.github.io, we've tried to lay this out from the scratch for everyone so that it's accessible. So when you're designing these consensus protocols, there are many different scenarios you can consider and many different outcomes you can consider, right? So one thing is, when you're thinking about these server replicas being what kind of a fault can creep in ever, right? So a simple one is where a server just crashes. So if you're using 10 servers, if one server crashes, maybe it's fine and we can still run this. A different one can be the server has an omission fault where some of the messages the server is sending does not reach. The more common one that we think about today is one where the server is Byzantine, where it can just do arbitrary things, or some subset of servers can do arbitrary things, and the goal is to tolerate, some subset being Byzantine or arbitrarily malicious. So depending on a lot of other settings, most of the protocols today are tolerant against 1/3 of these Byzantine faults or 1/2 Byzantine faults. So that's one angle with respect to what an adversary or can do in terms of the fault of a processor or a server itself. Then you have another aspect that is that has been dealt with in a lot of detail or a lot of rigor, and that is the network connection across different servers. Can we think of this network connection as so for one, I think we assume reliability, but in addition, can we assume that when a message is sent, it arrives within a fixed amount of time? So can I say any message that I send between any two servers will always reach within 10 seconds? If so, then we think of the network as being synchronous. Okay, so synchronous is a strong assumption, although for the most part, Synchrony largely holds today. Right. So if you have, for example, if you have a Synchrony and if you're trying to tolerate Byzantine faults, then you can actually tolerate 49% Byzantine faults. So I mean, very roughly speaking, a protocol like Bitcoin or so a protocol like Bitcoin, the reason why, so it's 49% hash power, so I think that's a very different dimension, but the reason why you can't tolerate 49% hash power, 49% adversaries, is because you are assuming synchrony, although you assume these faults can be malicious. So the other extreme is what is called as asynchrony. And if you have asynchrony, then all you say is a message that is sent will eventually arrive. There is no time bound whatsoever. And back in the 1980s, it was shown that, for a deterministic protocol, under asynchrony, you may not be able to, so there can be executions where you will not commit anything if you assume asynchrony, even if you have a single fault. So this was back in the 1980s, but this was, so two things. One, this was shown for deterministic protocols. And second, this is assuming a very strong adversary. So since then, the literature has evolved in two ways. One, in the asynchronous world, people have considered randomized protocols in addition to deterministic protocols. And so a lot of the asynchronous protocols that you see today are randomized because you want to tolerate Byzantine faults. The other literature that started developing in 1988 is based off of this model called partial synchrony, which is somewhere in between. And I guess a bunch of these subsequent protocols that we see today, be it PBFT, be it Tendermint, be it Hot Stuff, and many of the others, they are in this partially synchronous model. So partial synchrony is somewhere between synchrony and asynchrony, where you say the network can be asynchronous for a while, but eventually you will have this time frame where the network is synchronous and you will start making progress. So that is the key idea, because of which you can circumvent this impossibility, the FLP impossibility that I mentioned earlier, and you can still tolerate 1/3 Byzantine faults. And if you think about it intuitively, that model also makes sense in the sense that, yes, your network at some point can be really bad, but eventually, or for the most part, we enjoy good times too. So Byzantine versus, so the kind of faults on the nodes and network failures are I believe, two key aspects that we consider when we are trying to break down consensus protocols. There are many others in terms of the kind of adversary you're tolerating, the kind of participation level there is. So there are many other factors, but perhaps I'll not get into all of that right now. And we can take that as the discussion progresses. I guess the other side of things that I want to bring up is, what are you trying to optimize upon, or what are you trying to improve upon in this process, right? So the core metrics that traditionally we have attempted to improve upon and which are relevant even today are metrics like latency, communication complexity, throughput of the protocol. So in terms of latency, again, for deterministic protocols, there are lower bounds. You need to have T+1 rounds of communication if you have T Byzantine faults. But again, this is for deterministic protocols, and in most cases, based on some assumptions, of protocols that can do better. For instance, you think of what happens when you have, quote unquote, you heard of there being an honest leader, and if you have an honest leader in the protocol, the fact that you can commit much faster. Similarly, with communication complexity, it is known that protocols need n-squared communication if they are deterministic. And from there is a literature that has developed which has tried to reduce this communication complexity all through in these protocols. And finally, throughput is kind of a derivative of communication complexity and how the protocol follows. So I guess from a system standpoint, there has been a lot of work in improving the throughput of these protocols as well. So, I mean, I'll perhaps stop here. There are a lot of things that I can say, but I think I'll stop here and then we can iterate from here.
Definitely, that's a really great description and insight into this. Manmit, is there something that you want to add, maybe, or?
Yeah. So Doctor, my follow-up question was going to be around the classical approaches versus the new algorithms that we're seeing in the partial synchrony model, but So Dr. Naik seems to have covered that briefly already. I feel like the two camps that we have over here are the Starkware camp, which is working on Tendermint for Madara, which is our app chain framework. And then there's the Nomos network trying to go with hot stuff, being ambitious, making a lightning fast network. And I suppose from the developer's perspective, people might be interested in learning about the pros and cons of either, and why, Luke, at Web3MQ, you're choosing to go with this approach with hot stuff, and exactly which derivative of hot stuff you're using. I know we've spoken about this in the past with like chained hot stuff, but I'd love for you to perhaps give a brief overview of that. But before that, I want to kind of move the spotlight over to Itai for a bit, and Matan, and ask about Starkware's app chain tooling, and why you've chosen to go with the stack that you've chosen to go with.
Sure.
Are you asking about the app chain or about this core Starknet itself?
The app chains for now.
So the app chain is why we chose to go with the Madara. Is that the question?
So why we chose to go with Tendermint for Madara, and do you think that's still a good choice?
So basically, we were looking for a battle-tested protocol. Consensus is a very delicate matter. Even Tendermint, the initial paper, had to be revised because they found some corner cases later. So, but nowadays it is battle-tested. It is used in Cosmos. So that was one factor. The other is, I think, what we didn't need of a protocol. So we don't need, because we're layer 2, because we have the ZK proofs, the Stark proofs, we don't need a big consensus. Okay, we can use a small consensus and we don't lose security. And by using small consensus, we can use more powerful machines, which means more transactions, which means, higher supply and therefore lower costs. And therefore, because we have a small consensus, we don't need a consensus protocol that tries to cater for a large consensus. And Tendermint fit the bill. So it's simple, it's stable, it works well for a small consensus. And so that were the main reasons why we chose it.
Would it be, if I may just jump? Oh, sorry, Matan, go right ahead.
Oh, I was just going to say that for sort of trading off against another consensus like hot stuff, for instance, my understanding, and I will admit that my understanding of hot stuff is not as deeply I understand Tendermint at this point, is that the responsiveness has to do with how quickly you can recover in case there are errors, is the general direction. And from talking with the people who have experience with this in Cosmos, they see that well over 99% of their blocks are determined within the first round. And so we worked on the assumption that practically this would not be needed in most of the blocks. So Tendermint there is not, shouldn't limit us very often, at least.
Luke, would you like to add something? Make your case.
Yeah. I can definitely kind of also share too. I mean, for us, the situations was a little different. Our restrictions and places where we're kind of free to play, like obviously, for Starknet mainnet, right? There's a ton of people already using it. You have to be responsible, right? And for kind of these app chain frameworks, well, it's new. Every app chain kind of starts from a clean slate, so you can kind of be able to afford having something that's slightly newer and iterating from there. So that's kind of an area that was different for us, where we could take more risks. And kind of also, one of the decisions for us, why to choose that responsiveness, which is still, people still argue, right? It's a theoretical property, is it really that useful in production instances, whatnot? So for us, the reason we thought it was going to be important for Appchains was that we kind of imagined the environment for running these things or these nodes to be far different. Like for StarkNet mainnet, for example, generally it would be stable, right? It would be either StarkNet itself or partners that have good, guaranteed environments to run these kinds of things. For Appchains, right, generally it's not. It's going to be more mid and long tail. So we thought, okay, then something that was a little bit more able to at least be forgiving of that, we thought was good. So that's why we went for hot stuff, which is basically the biggest kind of I guess difference is that hot stuff is responsive, right? Tendermint still has fast instant finality. So yeah, that was kind of how we initially made our decision. We're kind of I would say we finished a first implementation, but also and this might also be kind of just sharing some of the hardships of hot stuff that might also be good things to consider over whether it's worth updating or switching over. Hot stuff pacemaker is somewhat complicated. This is the part that we haven't finished for the Madara stack yet. So the first implementation that we've already released that has the 3-phase whatnot voting and commitment, but that pacemaker part we're still working on that. So it turns out this is a little bit more complicated. And so that might be things to consider. But yeah, originally for us, the key decision maker was having something that's a little bit more tolerant towards mid and long tail node operators and sequencer operators. So yeah.
I kind of want to jump in here with this thought that someone at Starkware posted on Twitter a few weeks ago that ZK compensates for decentralization. And we're seeing so many more app chains and a bunch of Web3 infrastructure being built in that sense, using validity proofs. And I'm curious to get Dr. Naik's thoughts on how you see consensus solutions shaping up in this increasingly smaller, fewer node kind of environment, where people are using either off-chain solutions and settling validity proofs on chain, etc. So I'm just curious to see to hear your take on that.
Sure. So but before I get into that, I want to maybe set the ground for, I guess, how the two protocols are different and when you would want to use one versus the other, right? I think maybe just going back, in history, I guess both of these protocols are actually derivatives of what is called as the PBFT protocol. I mean, so when I say derivatives, so I'm thinking of this very conceptually, right? So PBFT was a protocol which people think of as the first practical protocol. It was by Castro and Liskov. And the idea over there, I mean, it was not, at least back then, I don't think they were thinking about the blockchain setting. They were thinking about a few server setting where you have tens of servers running these systems, right? And you're tolerating single-digit faults. The idea over there was you have a leader, and the leader is going to stay as the leader of the state machine replication system for a while and keep executing requests. And at a very high level, whenever it receives a request, it will get responses from a lot of parties. And because you're living in a partially synchronous model, it turns out that you need at least 2 rounds of votes from parties. And that is when you can commit or finalize this request. And every so often, it can so happen that the leader fails, it crashes, or the leader is not able to reach everyone. So there can be a network failure, or there can be a node failure. And whenever that happens, you want to switch this leader. So the world where the leader stays the same is called as the steady state, because you steadily just keep committing blocks or keep committing transactions. And whenever this leader fails, you say, we call this a view change, where you're changing the overall system parameter because you're trying to move to a new leader. So you can think of a view as being the reign of a leader in that sense. So you're trying to switch to another leader. And when a new leader comes in, this new leader has to figure out exactly what has it has to figure out exactly what the previous leader did, because there may be scenarios where the previous leader committed on something that not everyone is aware of. And at that point, this new leader needs to propose the same thing so that you can ensure everyone commits on whatever the leader has said. Right? So this was the protocol, and this protocol, it turns out, in the steady state, it required at least quadratic communication. And the view change step is where when a new leader comes in, how does it convince everyone that it is doing quote unquote the right thing? The basic principle over there was it would request a lot of status messages of what everyone has done in the network, and send a vector of n or order n messages to everyone saying, hey, this is what a large number of you have done, so this is how we should proceed. So I think that was a proof that it would send to every party on what it should be doing. Okay, and this made the communication of this protocol when you do a view change super quadratic. So it was, I believe it was cubic. Okay, and that can be, so when n is small, when n is in a few tens, that this is not a problem. But as soon as you start talking about n being in hundreds, it is a problem. So I think from a complexity standpoint, that is, or efficiency standpoint, that is bad. But it's also bad from the standpoint of how difficult it is to send these proofs and so on. So there was this line of work which tried to improve the communication complexity of these protocols, and Tendermint is one such protocol. And in my view, the key improvement that Tendermint did is it said, whenever your leader is going to change, at that point, I'm not going to send this big proof, but instead of sending a linear sized proof, I'm going to just send an order one sized proof. And that made things much better, both conceptually as well as from the perspective of communication complexity. So Tendermint, I think, made that big improvement. But as I believe either Luke or Rita or someone pointed out, this initial design, at least the way it was, it had some flaw with liveness violations. And I guess so. It is at this time that a group of researchers at VMware Research said, can we address this, and can we solve this problem? And that is when they came up with hot stuff, where they fixed that problem, one. But in addition, they said, if you are so in PBFT as well as in Tendermint, you require quadratic communication on each instance at each point. Whenever a leader is sending a message, and when everyone sends a message to everyone else, that's quadratic communication, and that can be bad. So the improvements were, they achieved what is called as optimistic responsiveness. And a second improvement that they did was required only linear communication across different parties. Okay, so that is the high level difference between the two protocols. So what is optimistic responsiveness? So typically in consensus protocols, so optimistic responsiveness basically says, I can move at the speed of the network. So whenever I receive a set of messages from the PS parties, I can simply move. I do not have to wait for a time bound to expire before I move on. So it enables, speed in terms of how fast you can move. So as an example, in Ethereum today, you have a block every 12 seconds. So that is a protocol that's not optimistically responsive, because even if the previous block arrived within the first 100 milliseconds, I still cannot propose the next block soon enough. I have to wait for the time bound to expire, and that can be bad from two perspectives. One is, it slows down the system, and second, you need to parameterize these 12 seconds to ensure there is sufficient amount of time for these messages to arrive. Right? If this parameter is incorrect, and if it takes actually even longer, then the system would not function correctly. So optimistic responsiveness basically says, whenever things are fine, so the optimistic over here is, a set of conditions that you can lay down. So whenever some good conditions hold, let's say the leader is good, then we can actually move as fast as the network dictates. And that is the property you get. So my understanding is that the original protocol Tendermint was not optimistically responsive, but perhaps the newer version does support optimistic responsiveness. So I think in that sense, the key difference between the two is, Tendermint does not give you it has this quadratic communication complexity, whereas hot stuff can do it in linear time, where your only communication is leader to everyone, everyone to leader, and so on and so forth. I mean, there are other differences with respect to support for pipelining and not. So those differences exist as well, but at least in my view, they are perhaps lower order differences. Yeah, and finally, I guess Luke pointed out about view synchronization. So the high level problem with view synchronization is for everyone to stay in the same view at once. I mean, very roughly speaking. And so why is this problem relevant in the case of hot stuff and not in the case of Tendermint? So generally, it turns out if you can have quadratic communication, then whenever I move to a view, a new view, I can send a message to everyone so that they can move to a new view as well. So if you have quadratic communication, this problem is relatively easier. But if not, that is when you need some special protocol to still maintain linearity and get view synchronization. And that's why you use this view synchronization protocol in addition with hot stuff. So I think that was one, but I guess Manmit, you asked a different question. Like I guess the question was with respect to how does execution change things?
Yeah, exactly. So we are seeing a lot of the new infrastructure that's being built around applications in StarkNet, taking things further away from on-chain execution and then simply submitting fraud proofs, validity proofs. I don't think have anything to do with fraud proofs, question mark. Yep, I just confirmed it. So and just submit validity proofs, and there's this idea that you're kind of just moving away from this world of consensus and shared finality to just executing off chain and compensating for decentralization with validity proofs. So that's my question. Like, how do you see consensus solutions keeping up with that trend, or how relevant do you think they're going to be in the up and coming times for a bunch of these app chains?
So to me, these are architectural differences in as far as the solutions go. I think that they're at a big picture, I guess they're still achieving the same set of guarantees, but architecturally they are different. So as an example, I think if I go back to the first thing that I said, I think you're trying to maintain the state machine replication system where you keep receiving these requests, and each of these servers would agree on these requests, right? And then they will execute upon these requests. So if I splice it in that way, there are three things that these servers are doing. One is whenever they receive a request, they need to ensure everyone has access to that request. So this is something that I call as data broadcast, where I mean, in the community, I guess different terms are used. I'm using this term data broadcast to mean that every party has access to the transaction that is being, or transaction or block, whatever you want to call, that is being shared. The second is consensus. So this is where the consensus protocol that we have been speaking about comes into picture, where everyone agrees on the set of or the sequence of transactions, right? And the third thing is execution, where you're taking these transactions and applying it on top of these consensus protocols, right? So this is one way to do things. But if you look at maybe something like, I guess, the Ethereum world with rollups, so they don't do exactly this. So what happens is, if with rollups, when you receive these transactions, right, you will you would be okay, in a rollup currently with the centralized sequencer, you receive these transactions and you process these transactions, and you send a proof to the Ethereum chain, right? So it can be fraud proofs or ZK proofs, and so on. But if you would want to, so I think one way to view this is, if you would want to decentralize this sequencer, right? I mean, I guess I'm maybe borrowing a little bit from what I understand from what Espresso is doing. I think if you're thinking of a shared sequencing model, and you have decentralized it as well, at that point, the splicing of these three tasks are look a little different. How? So if you think about what the shared sequencer is doing, it is responsible for agreeing on a sequence of transactions. But the sequencer itself is not responsible for executing the data, executing these transactions itself, because there's something. So there are some other servers which are responsible for execution and sending state proofs to Ethereum, right? So in that sense, if the sequencer nodes, if they do not need to execute, then perhaps they do not need access to all of the data itself. So you may just need some sort of a hash of this data, and agreeing on that suffices, right? So, but at the same time, if you have agreed on a sequence, but this data is not available, that is not okay either, right? So instead of every party holding the exact set of transactions or the entire block, what you can do is you can hold a portion of it. Think of it as a share of it, in such a way that you're not holding the entire block. If it's a 1 megabyte sliced block, you're just holding 10 kilobytes worth of information from it. But the remaining other nodes will also hold different shares corresponding to this. So together as a network, we will hold the entire data so that anyone who requests it can still get it. Okay, so if I were to think about the three things, so over there you needed data broadcast, where every node had to maintain, let's say in this example, 1 megabyte, had to store this 1 megabyte worth of information and ensure that everyone else has it. But in this new world, you do not need that, because all you need is data availability, where the set of nodes together need to maintain just 1 megabyte of information. Okay. I mean, the mechanism to achieve this can require you to store maybe 2 megabytes or 3 megabytes of information. But even if you have 1,000 nodes, you're not storing 1,000 megabytes of information. So your data storage in that sense reduces. In terms of consensus, it's still the same. You're still trying to agree on a sequence of values. Over there, it was the transactions directly. And over here, perhaps it's commitments or hashes of these transactions. Right? And in terms of execution, the server nodes over there were responsible for execution. And in this new model, someone else is responsible for executing. So to me, they're trying to get you equivalent things, but using slightly different approaches at an architectural level.
Makes sense. Itai, has Starkware been working towards shared sequencing for Appchains on Madara? I'm curious to hear Starkware's thoughts on the roadmap and progress there.
No, we don't have this in our roadmap. Basically, the idea is that you will be able to sequence the transactions that you want, and no need for sharing. But of course, we will be glad for any innovation from the community, or like Luke mentioned, I think they are thinking of it, so it would be welcomed. And I think that the proofs helped in this sense, because at the end, for example, we have our Sharp service. Sharp is a shared prover, and what it does is it takes basically executions from different chains. Nowadays, it's also the StarkX product line, and it combines all of them. So basically what proofs achieve is compressing computation, right? It's like zip to a file. Proofs are to computation. And the more computation you take, the better you can compress it. So by using Sharp, we achieve a better compression for all of the users and customers. So Stark proofs help in this sense as well.
Makes sense.
Yeah.
I did want to mention though that Dr. Knack mentioned sort of like distributed state where nodes hold parts of the data, and that's not the direction we go with. We, in our mind, nodes, again, because we rely on the base layer, Ethereum security, we can require nodes to be very powerful, cloud clusters, and so they have no problem holding all the state. And the benefits, of course, is then responsiveness if they want to execute transactions locally, estimate fee, and that sort of stuff.
Gotcha. So I know that we're running a little short on time. I want to make a little bit of a pivot in the conversation and bring up this idea that Luke and a few other people in our ecosystem have been very excited about. I have been too, which is that of extending the abilities of Cairo to other blockchain ecosystems, other networks, and basically being able to add Cairo execution environments to Cosmos, Bitcoin, which is what Luke is working on. And Luke, I was wondering if you'd like to touch on that subject and how Web3MQ and Nomos are going to be contributing to that.
Yeah, so I guess just a real quick gist about that is, we wanted to also kind of test out, these app chains built on Madara Stack. And personally, I think, the crown jewel of the Starknet ecosystem is, right, it lies in Sharp and the whole Cairo programming environment that allows you to build these really ZK native. People are still building Solidity, and it's widely adopted, but it's hard because it wasn't really natively built for proofs, and so Cairo and the Sharp stack, I think, are truly crown jewels. And then also, with some resurgence of BTC, the one thing that's still lacking with BTC right now is, something that allows you to program, allows you to build these slightly more sophisticated DeFi protocols to take advantage of all that economic security that BTC really has, right? And I guess maybe also tying a little bit back to Manmit's previous question about, kind of the decentralization or not kind of debate. I kind of feel it's like decentralization and cryptography. These are like two pillars that support the same goal. And then it's kind of a spectrum you can kind of pick. The same goal, I think, is economic security, right? We used to just call it decentralization in the past, but I feel at least the industry has a more clear goal right now, which is, okay, we want better trust in these machine systems for the economic properties of it. So you could either achieve it with a lot of decentralization, or you could kind of compensate for that with a lot of really, really good cryptography, which ZK is, right? So if you have better ZK, then you could take away some of that decentralization need, or vice versa, right? If you have very primitive cryptography, then you can compensate for that with a lot of decentralization. That's kind of how I personally see. And BTC right now, I guess, there's still problems with BTC, but still, in terms of decentralization and permissionlessness, it's actually still the best ecosystem around. And obviously the asset price reflects the amount of economic trust and security that people have in that ecosystem. So we thought, hey, it'd be really cool if we could bring the state-of-the-art programmable ZK environment and try to merge that with, this maybe old and classic, but also still very, very trusted ecosystem that, direly needs more modern programmability to unlock more of that economic value. There's a lot of trust, but we want to unlock that too. So that's kind of the underlying thinking behind, how to, what we're trying to do. And basically, the work itself is actually essentially, how do we connect that Madara app chain to BTC in more strict ways possible? Yeah.
Awesome. I also have one question. Thank you for the response, Luke. I have a question, and mainly for everybody. And after that, I think we could wrap up. So my question is basically, what use cases are you most excited about regarding layer 3s and app chains? And we could go around the room and see what do you think. So anybody, feel free to pick up.
So Dr. Nayak has this article on decentralized thoughts, which goes, what are blockchains useful for really? I guess it'd be nice if you could do an abbreviated version for what are app chains useful for, really, because that's a burning question that people ask me all the time, and I find myself in one, maybe two, maybe three boats. So would love to hear your thoughts first. Yeah.
So I think I'll be frank. I think I'm I come I think on this topic from a very academic side. So I think when I say what are blockchains useful for, really, I think I'm trying to think about the overall cell of the concept itself, right? But at the same time, I guess with app chains, I'll be frank, I haven't followed it too closely to uh, to answer this question in a meaningful way and be honest to myself. So I think I don't want to be guessing around, and that's why I think I'll choose not to respond because I'm not an expert here.
I can say some things that I hope Appchains will achieve. So first off is capacity. So if you have a very popular blockchain, if a user, a specific use case, whether it's DeFi or games, will compete on the resources with others, and Appchains allows you to separate that and know you have a capacity for a specific use case. Then it rolls into maybe having more simple transactions, like, for example, games. If you want to settle a game state very quickly, very often, that's very important to have this capacity. And the other thing is similar to what we have achieved with the account abstraction that allowed the people to innovate, the underlying logic of accounts. I think Appchains will also allow to innovate in how the blockchain operates. So, using different payment methods and stuff like that.
I think that Itai sort of touched on this, but what I was thinking sort of relates back to why Luke was saying they were interested in trying hot stuff, is the idea that an app chain can really optimize things for what their use case is. So if you're gaming and you really care about tail latency, even when a block fails in round 0, for instance, then you can choose to go with a different consensus protocol that is meant to handle that. So it allows you to really tailor the execution environment for your use case.
Yeah, and I guess I can add a little bit also, which is in the beginning I kind of said too. I mainly see two areas personally I'm really excited about. One is kind of gaming, the other is DeFi. I personally feel app chains. If we were to kind of sum up the value, I would say it's around providing really, really high UX blockchain interactions. Like, we all need blockchain to be adopted, right? And UX is really important for that. But I think the one pain point is that for different applications, UX really means different things, and it requires different infrastructure supply. Like for games, you just want it to be really high performance, really fast, so high throughput, high liveness. Consistency, well, does a pixel or two matter? Sometimes that can be blurred a little bit. But then for DeFi, it becomes a little different, right? For DeFi, it's about, ideally we want something with, less, mercurial MEV, right? So we don't want these weird things to happen. And so with app chains, we could actually go into the consensus mechanism and change a few things around, because a lot of MEV is really kind of rooted in how the mempool works, the mempool broadcasting works. But you can't just change Starkware mainnet for a single DeFi protocol, right? So those are the things that I personally think app chains can really bring unique value, and I would be really excited around.
Perhaps I have a question, I think, Luke, off of what you just said. So do you believe that for different applications, the underlying layer should do different things? So, or in other words, I think, do you believe that it should be a layered system where, I guess, the underlying layer, the foundation is set in one way, and then everything follows? Or do you believe it should behave differently depending on the application that is running on top of it?
I think just simply differentiating for the sake of it might be less productive. If everything were to be able to run on one chain and it could solve every single need that we want out of the application perfectly, then that would be great. But we all know with designing systems, there's always parts of that triangle or square that we really can't balance everything out of. So that's also like a restraint of the universe, right? So I think in reality, it does come to, you have to kind of specialize. Ideally, we wouldn't want to bother, like, StarkNet mainnet. It's simple enough, right? But in reality, maybe there's needs that really need these app chains. And so I think, in doing these things, the needs might be really important. Yeah.
Great. Thank you all for all the responses. I think we could wrap up today's call. I think there's a lot of questions to be asked more, and we could continue this for another 2 hours at least. So maybe it's an interesting idea to turn this into a mini series, and we can talk more. But again, I would like to thank everybody for joining today's call. It was really a pleasure talking to everybody. And thank you, and wish you a great day. And thank you for the viewers as well.
Thank you.
Thank you
Bye-bye.
so much.
Thank you. Bye-bye.